So, hello, my name is Kami. I'm also known as Danny Frisk, and I'm here today to talk to you about Pwning BIOSes, aka sharing my story of the elevator journey from ring 3 to ring -2. So first of all, who am I? As said, I'm Kami. I'm a 19-year-old hacker from Finland. I have been pwning different kind of stuff for almost a decade now. During of those years, last few, I have been concentrating on breaking firmware, BIOSes, UEFI, and hardware. I'm a co-founder of a Finnish hacker group named K4m1, and at the moment I work at Silverskin as security analyst. So let's begin by describing what is legacy BIOS. So BIOS, aka Basic Input-Output System, is a computer program responsible of initializing hardware on early phase on computer boot. It is not standardized, and it's varying on motherboard to motherboard. So basically, I cannot say that this exact thing is always like this. All of the upcoming specific technical details are only considered true related to my own motherboard. So not only does the BIOS initialize hardware during the boot phase, but it also provides a bootloader different sort of descriptor tables and functionality that can be called via BIOS interrupts. As example, it will provide global descriptor table and interrupt descriptor table, later of which is used for calling functions for drawing simple graphics and loading disks and loading stuff from disks. In this specific case, the BIOS in view from hardware. So it was stored to a non-volatile flash ROM chip, as BIOSes often are. And it was accessible via SPI data bus. The access to the ROM chip happened first via North Bridge, then to the South Bridge, and at last to the SPI. And overall, it's quite simple, even though the technical details are more complicated. But this is enough knowledge needed for understanding this talk. So during the startup, BIOS should initialize also these devices, the North Bridge and South Bridge. But in this very specific case, the BIOS did not actually initialize them properly, meaning that the write access to the SPI bus was left open in South Bridge, meaning that the CPU can even, during normal execution, access the SPI bus, meaning that the CPU can control and read and write the contents of the SPI flash ROM, meaning that the CPU can modify the contents of it. The next technical thing we need to understand is system management mode. System management mode, aka SMM, is also known as ring -2. It is the highest privileged run level of the computer, and it controls all hardware on the machine. It is entered via system management interrupts, which are either caused by signal from motherboard or chipset, or a software signal from the CPU, which is normally only used for taking over the control of ACPI power management, and really, really rarely for anything else legitimate. It is practically the one ring that controls all other rings. So whenever the SMM code is executed, the normal execution of ring 3 and ring 0, aka user mode and kernel mode code, is stopped, meaning that when this code is being executed, all other functionality of the computer is hanged. This mode is considered so special that it lives in its own physically isolated RAM known as SMRAM. So it is not only prohibited most of the time to call it, but it also has its own specific area of hardware reserved only for this code. The next technical thing is SPI, Serial Peripheral Interface, which is used in this case for communication between motherboard and flash ROM chip. The SPI is synchronous serial communication, bus, which is often found from USB, UART, flash ROMs, EEPROMs, Ethernet, and all other sorts of devices, and it's really common in embedded hardware. The communication between SPI master, aka in this case motherboard, and SPI slave, aka the ROM, happens in a way that the master first sends a clock cycle via SCLK. After that, the communication happens in cycles in frequency defined by that clock. And all read operations from master, as well as all write operations from master, happen via MOSI channel. And during that happens, every single time also read or write happen via MISO from slave to master. So every time master sends anything, it will also read something. And every time it reads anything, it will also write something. BIOS should always prevent ring 0 and ring 3 code from accessing the SPI BIOS ROM chip. But in this specific case, as said, it was left open. It can be a feature because this allows us to update BIOS code really easily without need for rebooting or flashing the code with external programmer. But it also lets us write fancy BIOS malware. So what I did was that I first dumped out the BIOS of my computer, reverse engineered it so that I gained understanding of how it works in practice. After that, I developed a simple rootkit for elevating my privileges from ring 3 to ring 0, wrote my BIOS kit, which I wrote to the SPI flash ROM, and that's basically it. If I wanted it to be persistent, I could also patch this BIOS so that it logs write operations to the SPI flash ROM, meaning that once I write my malware into that ROM chip, the end user can practically never get rid of it without either having utility to flash it from BIOS interface, which I could also block, or the other opinion is to unsolder the ROM chip from the motherboard, use external programmer to reflash it, and then solder it back to the motherboard. And I personally have never even once met an end user who is ready to unsolder a chip from motherboard just to get rid from malware. So basically this means that once I have achieved this, I have full everlasting rootkit within the ROM chip of the motherboard itself. So as said, SMM is the most powerful run level, and that's the holy grail we are looking for. We want our malware to be located within system management mode interrupt handler, meaning that whenever system management mode code is called, our backdoor will get invoked. Meaning that whenever the machine boots up, or the kernel takes over the ACPI, anything related to power control happens, our backdoor will get executed. It is also quite easy to execute it ourselves by writing our interrupt code to parallel I/O port OXB2, which is commonly used for triggering SMIs from CPU. Our backdoor running in SMM is practically invisible for the OS kernel and all sorts of antivirus software. The only way the kernel can kernel can notice us is that it can measure the time delay between the moment it was last executing, when we got executed, and when it got control back. So the time difference between the time when it stopped and when it continued running. And it's quite unlikely that the user will ever notice some sort of like few milliseconds of delay within the process execution. So as said, we are invisible in here, practically. So the steps of my exploit were first to gain root access by row hammering the machine, meaning that I flip bits related to sudo, meaning that I can change my privileges practically from regular user to super user. After that, I reboot the machine, setting Linux boot parameter IO control to be relaxed. And I also, at this moment, added my normal user to have access to root functionality so that I can easily write to IO ports. After that, I wrote my there is a mistake in the slide. I didn't write coreboot.rom because I actually, during this week, got my own backdoor to work and my own BIOS patches to work. So I flashed the modified BIOS ROM back to the ROM chip. And after that, I basically just rebooted the machine. And there we go. I have my own SMM backdoor running within the BIOS ROM. Now, all there was to do was to enjoy my high ring -2 privileges. I don't know why would I need them, but now I at least have them. So the tools I used were Radar 2 for disassembling and reverse engineering the BIOS binary. I also tried using IDA Pro, but as its graphical tool, I was not able to understand how it works properly. So this was just way more convenient. I also used NDSASM, which is coming together with NASM assembler for just really quickly checking some minor parts of the code. HexEdit for modifying raw bytes of the binary, because I had to modify the checksum and magic value areas, and I didn't want to do it with assembly, so I just instead modified the raw bits of the binary. I also used NASM for compiling my patches, and then object copy for copying them to specific memory regions of the BIOS ROM. And at last, I also used external programmer, as I managed to break my laptop quite a few times during this. And if you ever want to do BIOS exploitation, you really want to get external programmer, because you are going to break your device. It's gonna happen sooner or later. So then I'm going to proceed on showing a demo. I first wanted to make this a live demo, but as I burnt my ROM from my laptop motherboard, it's not going to happen this time, because I didn't have enough time to order a new ROM chip and solder it into my motherboard. I also got another motherboard from my employee, Silverskin, but as it was inside of a PC computer, desktop computer, I didn't want to bring it with me here. So I instead just simply recorded my desktop during the exploitation. So hold on a second, I'll open up the demo. It's over there. So just quick explanation. At the right one monitor terminal, you can just see record my desktop. It's not a tool I used for exploitation. It's just a simple screen capturing utility. So at this moment, I am practically changing the voltages of condensators of DRAM, and by that way, I'm modifying the values of the memory, and by that way, I am trying to flip specific bits on a specific binary to gain root access to the machine. So practically, this exploit works by changing bit values by induction on condensators. It will take roughly 10 to 20 more seconds. If I knew how to edit videos, I could have sped this up, but not this time. So there we go. I got the root access. After that, I initialized connection to the SPI flash and erased it first, the BIOS region of it, which is from address 0x0020 to address 5FFFFF. After erasing it, yes, I'm writing the BIOS binary to it, verifying that it really got written there, and after that, reboot my computer. As I didn't have a proper camera to record my desktop during the boot phase, I cannot practically show you, but what can you do? Opening up the next demo. So what do I do here is that I use a tool that communicates with SMRAM and trigger, no, it communicates with Smi Handler, invoke a little SMM backdoor, and dump the content of the SMRAM to smram.binary. After that, I verify that smram.bin file is actually a data file, and then I just simply read 8 first bytes of the SMRAM region. Now, this is just a simple proof of concept, but I really should not be able to read SMRAM contents from ring 0 or ring 3, as I just did. It's not possible unless you have SMRAM backdoor or some external device to read it with, but software should never be able to read it. Now, as I still have quite a lot of time, I was thinking that I'll go a bit deeper into the work of SMRAM, Smi Handler, etc. As soon as I figure out how to exit from the full screen of Firefox. I'm really not very good with graphical stuff. It's a pain in the ass to use that. So basically, what is this Smi Handler is that it is a part of firmware code constantly running in background of the background job in the CPU. All that it does is that it waits for interrupt signal to get written to I/O port 0xB2. Once that happens, it should always hang the execution of ring 3 and ring 0 code, switch to 16-bit real address mode. So the computer CPU at that moment runs in 16-bit mode. After that, it will look for first instruction in address 3, hexa address 380000, and because of it's in 16-bit address mode, obviously it cannot use that huge addresses. So the first address part is located in CS segment. Rest is in instruction pointer. After that, it will continue in SMM mode, execute the functionality related to the system management interrupt it just got, and if and when the BIOS works as it should work, it will just simply ignore this, but in this specific case, we will continue execution until we get return from SMM. After that, we will return control for the ring 0, switch back to 32 or 64-bit protected address mode, virtual address mode, and continue execution. Now, the only thing that we really have to be careful about is that if we take too long to execute, the kernel may notice it, and at least Windows NT and Linux kernels, when they notice that SMM or some sort of other thing is delaying the execute largely, it will practically hang or panic the kernel. So I really had to spend quite a lot of time to optimize my code so that it runs fast enough so that the kernel doesn't freeze or crash. But yep, that's about it. I was really a lot faster than I thought, but that just means there's lots of time for questions. There are my contacts. Oh, and I forgot to give credit for Coreboot and CBIOS devs. Without them, I would have no idea how Smi Handler works. But thanks to their open source BIOS, I was able to figure out how it works. Crash for writing different blog posts about exploiting SMM on Lenovo laptops. Silverskin for another motherboard, and Salihun for his awesome book on undercovering BIOS reverse engineering ninjutsu or something like that. But then, do you have anything to ask? Yes, go on. However, do you want to proceed?
How long did it take you, including the research phase, to develop this exploit?
Around 11 months, roughly.
And which part was the research in time?
Reverse engineering BIOS was definitely the most time-consuming phase.
Do you have any idea about how many computers are affected by this? I mean, you said that there shouldn't be a way to access the SPI, and in this case, there was a way to access it, but how many computers roughly have the same fault?
I have no idea, but so far every single... Actually, I cannot reveal the product manufacturer names because of legal issues, obviously, but every single laptop I have had so far has this same little feature. So the only thing that I haven't been able to exploit so far has been Apple laptops, because they have write-once chip that will literally break if I try to modify the chip, meaning that the computer is useless after that. At least those that I saw were working like this. Anyone else?
How about implementing the exploit? Do you need to have physical access always, or is it OS dependent? Does it work for all the operating systems?
As soon as you have any sort of access to the device, you can do this. If it's vulnerable, you don't need physical access. If you just make the backdoor really work and test it on your own device, you can do this remotely. You just have to gain first initial attack vector to get access to that machine. Someone else? Anything? Yes?
Is there any way to detect this attack? You said that you already optimized it so kernel won't crash, but any other signs, side effects?
Can you please repeat? People there are so loud that I didn't.
Sorry. Is there any way to detect that you got exploited this way? You already said that you optimized so kernel won't crash, but maybe any other side effects?
The only practical way of detecting this sort of attack that I am aware of is only the way that kernel measures timing. So I'm not aware of any another detection mechanism at the moment. Anything else?
Yeah, thanks for a great talk. Would it be possible to, or how hard would it be to write a tooling around it to practically like weaponize it?
Way over my skill set. I'm not aware how to do it. Like, it requires to reverse engineer the BIOS to understand how it works because it's different from device to device, like to manufacturer to manufacturer.
Yeah. Okay. Another question about the detection methods. Would it be possible to pretty much like hack your own BIOS and plant a BIOS canary?
I don't say that it's impossible.
Okay, thanks.
Anyone?
You said that in addition to developing the rootkit, you also patched your BIOS against someone else rooting your machine.
Yes.
So that probably would work as a detection mechanism to see if it's impossible to write there. And if not, somebody has maybe planted something there.
I, again, didn't quite hear because of
Could it work as a detection mechanism that somebody has already written something there if you cannot apply the patch?
It might work as a detection mechanism, but as some BIOS developers still lock their BIOSes, it's not an exactly reliable way to detect this. It may be done by BIOS vendor themselves. Anyone else wants to ask something? I suppose not. Well, Kay, and thanks. Bye.